Okay, I'm Heber. This is Holly Bond. This is our presentation of Experiment 1, the absorptions of cobalt-2 fluoride.
So the introduction, the outline, we'll be going over our introduction, experimental results, discussion conclusions, and our references.
Okay, these are the different purposes for this lab. First one was to find lambda max of the cobalt-2 fluoride. The next was to make a standard curve for the cobalt-2 fluoride. And then at the end we had two different unknowns, and we used our standard curve to find these two unknowns.
A method was used in this experiment called spectrophotometry, and this simply is the relationship between the amount of light absorbed and the amount of substance present, and these two variables had a direct relationship.
Okay, these are a few definitions to help understand the lab. First is the absorption spectrum. A substance can have it can either emit light or absorb light depending on what's inside it, the concentration. The higher the concentration, the higher absorption, and vice versa. And then the spectroscopy. This is taking the spectrum of the substance and using this to find the molecular properties of the substance.
So experimental, this is how we did the lab. Our first step was to find the lambda max of cobalt-2 fluoride, which was done by using two cuvettes. One was full 3/3 of the way full with water, which was our blank, which was used to calibrate the spectrophotometer, which I have shown here at the right. The second cuvette was full of cobalt-2 fluoride, which was put into the spectrophotometer, and the absorbency and transmittance readings were taken at various wavelengths. We started at 400 nanometers of light, and we measured them all the way up to 600 nanometers of light by increasing increments of 25. And the lambda max was found at the highest absorbency reading, which was 0.806, and our lambda max turned out to be 500 nanometers.
Okay. To further the experimental, this was when we created our standard curve by making 8 different dilutions. We did this by taking different amounts of the concentration, or different amounts of cobalt-2 fluoride, and then combining it with different amounts of water. And then these dilutions were then placed inside the spectrophotometer and read at different wavelengths. And we determined that lambda max was 500 nanometers. Then after the absorbency and transmittance values were recorded, we then used this to find our unknowns.
So this is our results. The first table is our determination of lambda max. And as you see, this table shows the relationship between wavelength, transmittance, and absorbance. As you can see, transmittance here decreases as absorbency values continue to increase until the lambda max of 500 nanometers. And then percent transmittance values started to increase as absorbency values started to decrease, showing an inverse relationship.
Alright, this is one of our example calculations. This was a calculation for absorbance. As you can see, absorbance, the calculation for it was 2 minus the log percent transmittance. And then we just plugged in our percent transmittance, which was 88.0, and we got absorbance to be 0.0555.
So this is our absorbance spectrum that we found. As you can see, it displayed the relationship between absorbance and wavelength, and they have a direct relationship. As wavelength values increase, absorbency values increase until the lambda max of 500, and even though wavelength values continue to increase, absorbency values decrease.
Alright, then table 2 represents the construction of our standard curve. As you can see, we created our 8 different dilutions. We added different amounts of cobalt-2 fluoride and decreased the amounts of water to give us more concentration in the lower test tubes, and then higher concentration as we go.
So these are our two example calculations. The top one is for molarity of test tube number 3, and the bottom equation was for our constant or epsilon calculation for test tube number 3. For the first calculation, we used the equation molarity concentrated solution times the volume concentrated solution equals the molarity of the diluted solution times the volume of the diluted solution. And we manipulated the equation and we got MD, because that's what we were looking for. We were looking for the molarity of the diluted. We just plugged in the numbers and we got the molarity diluted solution to be 0.0600 molarity. And then for our epsilon calculation, or the constant, we did Beer's law, which is absorbency equals epsilon times concentration times path length. And then we just manipulated the equation to get epsilon by itself. And we solved for it, and we got 4.98 liters per mole times centimeters.
This figure represents our standard curve. As you can see, we have absorbance on the y-axis, concentration on the x-axis, and as these two increased, we get an overall positive slope, contributing to our overall finding that absorbance and concentration have a direct relationship.
So table 3 is our determination of the concentration of the unknown solutions, and we have the unknown numbers 10 and 11. And we put these into the spectrophotometer, and we took their transmittance and absorbency readings at the lambda max found in the beginning of the lab. The percent transmittance of unknown number 10 turned out to be 22.6%. The absorbency was 0.646. Unknown number 11 was 45.6% transmittance, and absorbency was 0.42.
And then these are the two calculations of our unknown substances. As you can see, we took the slope-intercept form, which we got from our standard curve. Then we took the slope-intercept, and we put it into our calculation for the unknowns, which was absorbance is equal to epsilon times path length times concentration plus the slope-intercept, or y-intercept. And then we just plugged in what we have, which we have the absorbance, and we were solving for the concentration. So then we just manipulated around to solve for the concentration. We ended up getting 0.130 molar for unknown number 10. And then we ended up getting 0.0710 molar for the concentration for the boiler.
Our discussion and conclusion section. The first question asked us to determine the relationship between percent transmittance and absorbency, which, based on our conclusions, we have concluded that it has an indirect relationship, and this can be seen in table 1. As you see here, the values for transmittance decrease as the absorbency values increase until lambda max of 500 nanometers, and then transmittance values decrease and absorbency values increase, showing that indirect relationship. It also can be seen in table 2. Here we have the same trend, percent transmittance decreases as absorbency values increase. In question 2 asks us if our selection of lambda max was correct, which we said yes, it did support our selection of 500 nanometers, because the max absorbency of 0.806 was found under 500 nanometers of light, and also our unknown concentrations fell within our line of progression.
Okay. For number 3, this asks to give the relationship between the absorbance and concentration, which we determined to be a direct relationship based on our data in our tables. As you can see, as the concentration increases, so does the absorbance at lambda max, which is 500 nanometers. And then this pretty much represents what I just said. As the absorbance increases and concentration increases, we have a positive slope, so that represents our direct relationship. And then number 4, this just asks to give our overall findings for the lab. And we found lambda max at 500 nanometers. Absorbency and concentration have a direct relationship. Percentage transmittance and absorbency have an indirect relationship. And the concentration for the unknowns 10 and 11 are as follows: 0.130 molar, 0.0710.
And these are references. We've referenced our lab manual as well as the online chemistry textbook. Thank you.